Okay, so we said that we will look at the properties of divided differences. So I just recall, while constructing the divided difference interpolating polynomial, we had constants a0, a1, etc., an. We explicitly showed that a0 is the 0th order difference, a1 is the first order difference, the a2 is the second order difference, and so on, an is the nth order difference. And we denoted the nth order difference by f of x0, x1, x2, etc., x3, xn, and we said that an is this. So how are we going to obtain this an from the difference, divided difference table, or what is it actually? So just as the first order difference is expressed in terms of the 0th order difference, the second order difference is expressed in terms of the first order differences, and so on. The nth order divided difference is expressed in terms of the n minus 1th order divided differences, and we show this property, namely the divided differences satisfy the property that the nth order difference f of x0, x1, etc., xn is f of x1, x2, etc., xn starting from here minus f of x0, x1, etc., going up to xn minus 1 divided by xn minus x0. So let us show this property. So this will tell us how the higher order differences, divided differences, can be computed when we know the previous order divided differences. So to prove this result, so this is property 1, where we need to show that the divided differences satisfy this property. So to prove this, let us denote by pk of x, right, or let pk denote the interpolating polynomial of degree at most k that interpolates the function f of x at points x0, x1, etc., up to xk. So we are given information at k plus 1 points. So we can seek a polynomial of degree at most k that interpolates the function at these points. And let q denote the interpolating polynomial of degree at most n minus 1 that interpolates the function f of x, say at the points x1, x2, etc., xn. How many points are there? There are n points. So we can seek an interpolating polynomial of degree at most n minus 1, and that we denote by q. So let us write down the properties explicitly. That is, what does pk do? Pk at xi is f of xi for what? For I is equal to 0, 1, 2, 3 up to xk. And what about q? Q at xi is f of xi for I is equal to 1, 2, 3 up to n. That is how we have denoted the polynomials, interpolating polynomials. If this happens, then we will now show that Pn of x, a polynomial of degree at most n, that interpolates the function at x0, x1, etc., xn is q of x plus x minus xn by xn minus x naught into q of x minus Pn minus 1 of x. So, we first show this result, and from here we deduce the property of the divided differences. So, what is it that we want to show? We want to show that a polynomial of degree at most n that interpolates the function at n plus 1 points can be given in terms of this polynomial q and a polynomial of degree n minus 1, and then the term that is added to it has as a factor x minus xn in it. So, let us look at the expression star and see what about the left hand side. Left hand side is a polynomial of degree n. How do I say that? I have given already the notation. By pk I mean the interpolating polynomial that interpolates the function at x naught, x1, etc. xk, and it is of degree at most k. So, that notation tells me that Pn of x is a polynomial of degree at most n that interpolates the function at what points x naught, x1, etc. xi, I mean x naught, x1, etc. up to xn. So, I know that the left hand side Pn of x is a polynomial of degree at most n. So, now let us look at the right hand side and see what it represents. The right hand side, if you see, I have q of x, I know it is a polynomial of degree at most n minus 1. So, that polynomial of degree n minus 1. What about Pn minus 1? Pn minus 1 is a polynomial of degree at most n minus 1 that interpolates the function f of x such that Pn minus 1 of xi is f of xi for I is equal to 0, 1, 2, 3 up to xn minus 1. So, this is a polynomial of degree n minus 1, this is a polynomial of degree n minus 1. So, the difference is a polynomial of degree at most n minus 1, and that is multiplied by a factor x minus xn. So, the second term is a polynomial of degree at most n. So, that is added to a polynomial of degree n minus 1. So, on the whole the right hand side is also a polynomial of degree at most n. So, the left hand side and the right hand side are both polynomials of degree at most n. So, let us now see what are the properties of the polynomials. Let us look at what is Pn of xi. So, Pn of xi is q of xi plus xi minus xn by xn minus x naught into q of xi minus Pn minus 1 of xi. So, I would like to look at this for I running from say 1, 2, 3 up to n minus 1. Let us first focus on these points. What are they? x1, x2, etc. xn minus 1. What is Pn of xi for I is equal to 1 to n minus 1? Just see, Pn of xi for I is equal to 1 to n minus 1 will be f of xi. So, the left hand side is f of xi. What about q of xi? What does q do? Q of xi is f of xi for I is equal to 1, 2, 3 up to xn minus 1 and xn, and therefore, up to n minus 1 q of xi is f of xi because it interpolates these at these points. So, plus xi minus xn divided by xn minus x naught into what is q of xi at these points? It is f of xi. What about Pn minus 1 xi? Pn minus 1 xi when k is n minus 1 will be f of xi at points 0, 1, 2, 3 up to n minus 1 xn minus 1, and therefore, this again will be f of xi, and so this results in f of xi is equal to f of xi. For what values? I is equal to 1, 2, 3, etc. up to n minus 1. Or I can write this as Pn of xi itself. So, Pn of xi is f of xi. So, the polynomial that we have written has the property that at x1, x2, etc. xn minus 1, it interpolates the function. So, let us see what it does at x0 and what its value at xn. These are the 2 points which we have not checked so far. So, Pn at x0 will be q at x0 plus, just look at this, x0 minus xn. So, substitute for x as x0 divided by xn minus x0 multiplied by q at x0 minus Pn minus 1 at x0. So, that will be equal to q of x0, first term x0 minus xn by xn minus x0. So, the first term will give you q of x0 and the next term will give you plus Pn minus 1 at x0. So, this says Pn of x0 is the same as Pn minus 1 at x0, and let us see what Pn minus 1 does. Pn minus 1 at x0, because Pk of xi is f of xi for I is equal to 0, that is it interpolates the function at x0, and Pk is a polynomial of degree at most k. So, Pn minus 1 is a polynomial of degree at most n minus 1, which interpolates the function at x0. And so, Pn minus 1 x0 is nothing but f of x0. So, what does it yield? Pn of x0 is f of x0. So, Pn interpolates the function at x0. Let us now take Pn at xn. What is Pn at xn? So, let us use this star and then find out. So, Pn at xn is q at xn. Then the next term xn minus xn. So, the next term does not contribute. Now, we look at q at xn. What does q do? Q interpolates the function at a set of points x1, x2, etc. xn. So, at xn, q of xn is f of xn. So, this is equal to f of xn. So, what is it that we have proved in these steps? We have shown Pn is an interpolating polynomial of degree at most n that interpolates the function at x0, that interpolates the function at x1, x2, etc. up to xn minus 1, that interpolates the function at xn. That is, Pn is a polynomial of degree at most n that interpolates the function f of x at a set of how many points? At a set of n plus 1 points, namely it satisfies the property that Pn of xi is f of xi for I is equal to 0 to n, and the left hand side polynomial is equal to the right hand side polynomial at all these points. Namely, we have shown that Pn of xi is equal to this not only at I is equal to 1 to n minus 1, but also at x0 and xn. So, we can write that Pn of xi is equal to q of xi plus xi minus xn by xn minus x0 multiplied by q of xi minus Pn minus 1 of xi for points I is equal to x0, x1, etc. up to xn. And left hand side Pn of x is a polynomial of degree n, the right hand side is also a polynomial of degree n, and their values match and give you f of xi for all these points x0, x1, etc. xn. So, left hand side is an interpolating polynomial interpolating the function f of x at the points 0, 1, 2, 3 up to n. Right hand side is also a polynomial of degree n that interpolates the function f of x at the discrete points x naught etc. xn, and therefore these two polynomials must be identical, because there is a unique interpolating polynomial that interpolates the function at a set of discrete points. So, these two polynomials must be identical. So, Pn of x and q of, and the right hand side, namely q of x plus x minus xn by xn minus x naught into q of x minus Pn minus 1 of x, right, are identical polynomials. Polynomials of degree at most n that interpolates the function f at a set of discrete points x naught to xn, and therefore coefficient of x to the power of n in both these polynomials must be the same. So, let us compute the coefficient of x to the power of n in Pn of x. Do you know what is the coefficient of x to the power of n in Pn of x? Just recall the divided difference formula. The last term had an nth degree polynomial, and the factors were x minus x naught, x minus x1 etc., x minus xn minus 1. So, the coefficient of x to the power of n is nothing but the nth order divided difference. So, the coefficient of x power n in Pn of x is the nth order divided difference f of x naught, x1, x2 etc. up to xn. So, we now write down the coefficient of x to the power of n in the right hand side of star. So, we look at the first term. The first term is q of x, which is a polynomial of degree at most n minus 1. So, this does not contribute. So, let us look at this. This is a polynomial of degree at most n. So, the coefficient of x to the power of n coming from this polynomial is going to be, see, x minus xn multiplies a polynomial of degree n minus 1, right. So, this higher x power n minus 1 coefficient multiplies the x term with 1 by xn minus x naught as the coefficient will give you the coefficient of x to the power of n. So, what is the coefficient? That is 1 by xn minus x naught into the coefficient of x to the power of n minus 1 in q of x. And we know q of x is a polynomial of degree at most n minus 1. Again, we recall the divided difference interpolating polynomial, and what is the coefficient of x to the power of n minus 1? It is nothing but an n minus 1th order divided difference, but what are the points at which q interpolates the function? At I, which is 1, 2, 3 up to xn, and therefore the coefficient will be f of x1, x2 etc. up to xn. That comes from the first term. What about the second term? There again Pn minus 1 is a polynomial of degree n minus 1. That multiplies the factor x minus xn, giving you a polynomial of degree n whose coefficient is going to be 1 by xn minus x naught, which is the coefficient of x there, into the coefficient of x to the power of n minus 1 in Pn minus 1. But Pn minus 1 is a polynomial of degree at most n minus 1 that interpolates the function where at x naught, x1 etc. x n minus 1, and therefore what is the coefficient there? It is going to be f of x naught, x1 etc. up to x n minus 1. So, these two coefficients must be the same. That is what we have concluded. So, what does it give? That gives you the left hand side is f of x naught, x1 etc. xn, and the right hand side is 1 by xn minus x naught into first term f of x1, x2 etc. xn minus the second term f of x naught, x1, etc., xn minus 1, and therefore that proves the property of the divided difference that we want to establish. So therefore f of x naught, x1, etc., xn must be 1 by xn minus x naught into f of x naught, x1, x2, etc., xn minus f of x naught, x1, etc., xn minus 1, proving the property of the divided differences. I hope it is clear from the argument, and therefore this property helps you to compute a higher order divided difference in terms of the lower order divided differences. So when you form the table, divided difference table, then the entries in each of those columns can be computed in terms of, so the higher order difference can be computed in terms of the lower order divided differences. Let us now prove the second property, namely divided differences is symmetric in its arguments. If you take a divided difference of a particular order, then it is symmetric in its arguments. What does it mean? Let us just understand. If I take the first order divided difference f of x naught, x1, the arguments are x naught, x1. The result says it is the same as f of x1, x naught. And that is obvious, because what is the left hand side? The left hand side is f of x naught, x1. By definition, it is f at x1 minus f at x naught divided by x1 minus x naught. I have used the previous property. When I take n to be 1, I have f of x naught, x1, and that is equal to, right, n is 1, so f of x1, minus n is 1, so f of x naught by x1 minus x naught. And what about the, what is f of x1? It is the 0th order difference, so it is the function value itself. So this by x1 minus x naught. So let us take the right hand side, which is f of x1, x naught. So by definition, what is it? It is f of x naught minus f of x1 divided by x naught minus x1. So I again use what the definition of 0th order difference. It is the function value at x naught minus x1 divided by x1 minus x naught, which is f of x1 minus f of x naught divided by x1 minus x naught, and that is the left hand side. So it is symmetric in its arguments. So what will be the result in the case of second order differences? F of x naught, x1, x2 must be equal to f of x1, x2, x naught, and that must be the same as f of x2, x naught, x1. Namely, when I cyclically change these arguments, so x naught, x1, x2, then x1, x2, x naught, then x2, x naught, x1, and form the second order difference, then the result is the same, is what this property tells you. So let us prove it in general. Namely, we will show that if I take the nth order divided difference f of x naught, x1, etc., xn, and then arrange these in cyclically in any other manner, then all these divided difference values will be the same. That is what we would like to show. It is symmetric in its arguments. That is what will have to be proved. So can you think of how we should show this? So we want to show the following. Show that the nth order divided difference, say f of z0, z1, z2, etc. zn is the same as the nth order divided difference x0, x1, x2, etc. xn, where z0, z1, etc. zn is a permutation of x0, x1, etc. xn. They are essentially x0, x1, etc. xn, but some cyclic permutation has been done. Just as one can show f of x0, x1, x2 is, so this is my x2, x0, x1, which I have called as z0, z1, z2. So these are essentially x0, x1, x2 arranged in some order. So now the proof must be easy. What do we do? Let us construct a polynomial of degree at most n that interpolates the function at the set of points z0, z1, etc. zn and denote by, say, Pn. So let Pn be the interpolating polynomial of degree at most n that interpolates the function f at zi for I is equal to 0, 1, 2, 3 up to n. And let me denote by Qn the interpolating polynomial of degree at most n that interpolates the function f at xi, I is equal to 0, 1, 2, 3, etc. xn. Remember, zi's are no different from xi's, they are just cyclic permutations of the xi. So they are essentially the same set of points at which the polynomial Pn interpolates the function f. So Pn must be identically the same as Qn. They are different, they are polynomials of degree at most n. Each one interpolates the same function f at the set of same points xi and zi, where zi is a cyclic permutation of xi's. So the two polynomials must be identical because there exists a unique polynomial that interpolates the function at a set of discrete points. And therefore, the coefficient of x to the power of n in Pn must be the same as coefficient of x to the power of n in Qn. What is the coefficient of x to the power of n in Pn? Recall the divided difference interpolation formula. It is the nth order divided difference. What is it? It is f of z0, z1, etc. zn. That must be the same as the coefficient of x to the power of n in Qn. So recall the divided difference interpolation polynomial. What is the coefficient of x to the power of n? It is the nth order divided difference f of x0, x1, etc. xn. So the coefficient of x to the power of n in both the polynomials must be the same because they are identical polynomials, and therefore these must be the same, and therefore the divided differences is symmetric in its argument, and that is how we prove the second property. So let us write down the details. So Pn is identically the same as Qn. Since both are interpolation polynomials of degree at most n, interpolating the function f at the same set of discrete points. So, therefore, coefficient of x to the power of n in Pn must be equal to coefficient of x to the power of n in Qn, that is f of z0, z1, etc., zn must be the same as f of x0, x1, etc., xn, and that proves the second property, that it is symmetric in its argument.